Hello, stat students. Today we are going to do 3.2b, Residuals of the least squares regression line. So as I mentioned in 3.2a, a residual is the difference between an observed, which is our actual value of the response variable, and the value predicted by the regression line. So the residual is equal to the actual minus the predicted. And remember that was A minus P, which is equal to Y minus Y hat. So going back to our like a trend line. So here's the trend line. And here are some actual points. There we go. Some I'll put closer there. So to find the residual, what we did was we drew a line from the actual point on the scatter plot, the actual value, to the trend line. And when the actual value is above the trend line, you have a positive residual. And that makes sense because if this is A and this point right here is P, then if you have a number like 30 and 30 minus 20, that's going to be 10. It's a positive residual. If you have a point below the trend line and you draw a vertical line, this is our vertical deviation. So here's actual, here's predicted. If you took a number like 8 minus a number like 10, you get a negative 2. So it'd be a negative residual. So how do we interpret the negative residual and the positive residual? A negative residual means we overestimated the response value, and that makes sense because we get a negative value and the predicted is bigger than the actual value. A positive residual means we underestimated the response value. And that makes sense because the predicted value is lower than the actual value. Okay, let's do a sample example. This is called back to the track. The equation of the least squares regression line for the sprint time x and long jump distance y data is y hat is equal to, so remember y hat is the predicted long jump distance, is equal to 304.56 minus 27.63 times the sprint time in seconds. Find and interpret the residual for the student who had a sprint time of 8.09 seconds. So sprint time is your explanatory variable, and long jump distance is your response variable. Oftentimes, students find the residual, but they don't interpret it, and then they miss points. So find and interpret the residual for the student who had a sprint time of 8.09 seconds. So the first thing we want to do is look in our table and find the actual long jump distance. So right here, so 8.09, that value, the value 151 is our actual long jump distance. So let's write our equation down. So y hat equals 304.56 minus 27.63 times, well, I'll go ahead and put in 8.09 because we want to know what the predicted value is, because we already know what the actual value is. It's 151. So y hat equals, if you do all the math, you get 81.0333. And remember, this is the predicted. So we can now calculate the residual. So the residual is the actual minus the predicted. So that would be 151 minus 81.0333. Subtract, and you get that the residual is equal to 69.9667. Remember, rounding is not a big thing. You just don't need to have like 10 digits after the decimal point. The residual is positive, and remember, when the residual is positive, we have underestimated the response value because the actual is higher than the predicted. Okay, so to interpret this, the predicted value is less than the actual value. So we underestimated. And what did we underestimate? We underestimate the response variable. So we underestimated long jump distance by 69.9667 inches. And that's interpreting. So it's really important that you know the what a residual is and whether something has been overestimated or underestimated. And just remember, if um, the point on your scatter plot is above the trend line, it is an underestimation. And if it's below the trend line, then it's overestimation. Okay. We can also calculate regression with means and standard deviations. So, in the last chapter, we talked about the five number summary and or doing the one variable statistics, and we were always given the mean, the standard deviation, median, Q1, and all that stuff. So, we know how to find the least squares regression line using the a plus bx function, our calculator, but we can also find it using means, standard deviations, and their correlation. Now, the formulas I'm going to give you are on your formula sheet. As a matter of fact, these round up basically part one of your formula sheet called descriptive statistics. So, this first equation is just your predicted value is equal to your y-intercept plus the slope times the variable x. So this is our regression equation. It doesn't tell you what the equations are. You just kind of have to recognize them on the formula sheet. These remaining two equations are on the formula sheet also. So on formula sheet part one. Okay, here we go. So the slope is B is equal to the correlation times the standard deviation of y divided by the standard deviation of x. And then lastly, the y-intercept is A equals y bar minus b times x bar. Now, this particular formula is not on the formula sheet, but a variation is they solve for y bar. So just add um, b times x bar to both sides, and you will get that. So those three are on the formula sheet. And just to let you know, this next little information is super important. It's on the multiple choice exams a lot of times. All least squares regression lines will run through the point X bar, Y bar. These are the means. So the way we derive this particular formula is as follows. So we take our regression equation and we replace y hat and x with x bar and y bar because all least squares regression lines will run through that point. So replace this with y bar equals a plus b times x bar. And then just solve for a. So subtract bx on both sides. You don't need to know how it was derived, but that's where you get it. So that's when we know the mean, we know the standard deviation x of our explanatory variable, we know the mean y of our response variable, and the standard deviation of the response variable. And correlation, then we can work with those and get some equations. So let's go back to our Honda sample. So the used Honda, the number of miles in thousands for the 11 used Hondas has a mean of 50.5 and a standard deviation of 19.3. So remember, number of miles was your response variable, or I'm sorry, was your explanatory variable. My bad. And the asking price, the cost, was the response variable. So there you know which one's X, which one's Y. Um, the mean of the response variable was $14,425 and a standard deviation of $1,899. The correlation for these variables was a strong negative correlation. It was negative 0.874. Let's write down the information that we um, are given. So X bar is 50.5. So remember that was in thousands. And then the standard deviation was 19.3. Y bar was 14,425. The standard deviation of the response variable was 1899. And we know that the correlation was negative 0.874. We need to find the equation of the least squares regression line. We're not given data. So if we're not given data, this is another way to do it. If we're given data, you can enter it in a list. Sometimes that takes too long. So the first thing we want to do is find the slope. Okay, so we're going to find the slope B. And so B is equal to the correlation times the standard deviation of Y, which is 1899, over the standard deviation of X, which is 19.3. So doing all that math, you should get B to be negative 85.996. We know slope now. Next thing we need to do is find the y-intercept so we can write our equation. Hopefully this brings back memories of algebra. Okay, so to find the y-intercept, we're going to use that last equation, A equals y bar minus B times x bar. So A equals Y bar is 14,425 minus B, and remember B is negative, so don't forget the negative, times X bar, which is 50.5. Okay, so this is going to become a positive here. I feel like I did something wrong. No, I didn't. Just looked like a bigger number than I thought. Okay, so A should give you, after you do all that math, 18,767.798. And looking back at our example, we got, using the calculator, 18,733.28, but that's close enough. It's close enough because, there's always going to be rounding errors and so on. Okay, now that we know A, now that we know B, we can write our equation. So our predicted cost is equal to 18,767.798, or you can round it to 80. Um, plus a negative 85.996, or minus 85.996x. And that is our least squares regression equation. All right. Explain what change in price we would expect for each additional 19.3 thousand miles. So the key word here is change. So when you think about change, we are interested in slope. So the slope is negative 85.996. And we know for each 1,000 miles, um, the price will be decrease 85.996. So we want to multiply by 19.3. And when we multiply those two, we get a negative 1,659.7228. So to summarize that, the price will drop $1,659.72 for each additional 19.3 thousand miles. And lastly, what happens if we standardize both variables? Well, if you remember about standardizing variables, we're going to change all of our values to z-scores. And remember, z-scores have a mean of 0 and a standard deviation of 1. So if we go back to our equation for slope is equal to r, and I'm going to replace the standard deviation of y with 1 and the standard deviation of x with 1, because remember, the standard deviation is 1 when we're standardizing. So that just becomes b equals r. Okay, so the slope is equal to r. Okay. For the y-intercept, we have a is equal to, we are going to replace y bar with 0, because the mean is 0, minus b, and b is r, times the mean of x, which is 0. So 0 times anything is 0, so we just have a equals r. So now our final equation for z-scores is y bar is equal to 0, which is your y-intercept, plus our slope, which is r, times the variable x. So this is for z-scores. Now, are you going to do heavy work with it? No, but just be aware that, or just understand that when you're standardizing something, you're always going to have a mean of 0 and a standard deviation of 1. And those are the notes for 3.2b. Have a great day, stat students.